the k equals 0 case before we get started on this one. We're supposed to show a very large quotient here is always going to be resolved to a natural number. So k equals 0 is easy to see. K equals 1 is already a pretty big computation. But this would imply that we have 2 to the, if you put k equals 0 right here, you would have 2 to the 4th, which is 16. So it's 2 to the 4th plus 3 over 19, which is equal to 19 over 19, which is a proud member of the natural numbers, namely 1. It's the first natural number, member of n, the set of positive integers, or non-negative, I guess, the way we're using it here. So now, let's take a look at another way to write this. I prefer to write this modular arithmetic format. Another way to state this would be to say that 2 to the 2 to the 6k plus 2, where 6k plus 2 is the exponent of that highest 2 there in this tower of powers. Okay. Another way to write this, it may be, I don't know, I like it. I'm more comfortable in this form here. Congruent to 0 mod 19. Okay. Or is what I'm saying is this statement right here is absolutely equivalent to this statement right here. This literally means take this, subtract 0, and if it's divisible by 19, that's what we're trying to show. All right, now you can see from the form that the 3 here, we don't want to drag that around, so it's clear that if we can show that this is congruent to 16, we'll be done. Okay. Now, y'all, this is a famous result, Fermat's little theorem, and an impact on why this is important is that once you know this fact, you can also state that 2 to the 18th raised to any power is also congruent. That's the power of modular arithmetic. It behaves much like equality. Let's call it m is also congruent to 1. And what you can think about here is just you can apply exponents to both sides of the equation. Let's call it an equation. Okay. This also is a consequence of the Euler Totient function. In fact, the Euler Totient function gives you Fermat's little theorem. But anyway, notice that this is in the form a to the p minus 1 is congruent to p. So here it's important. All we really need to do is reduce this much of it right here. Let me circle this, see if I can do that without distorting things. Okay. It's all about this exponent right here. So we're actually, I wrote that down right here. We're trying to reduce this. Now, another way of putting this, reduce perhaps is confusing. We're trying to go 2 to the 6k plus 2 congruent to r. Call it r. I haven't used that letter yet. And r would be a number between 0 and 17 inclusive. And those are simply the remainders when you divide by 18. That's why I'm using r for remainder. I just noticed that. Okay. Again, folks, note that if you divide any number by 18, you're guaranteed to get an integer between 0 and 17 inclusive, and 0 would be the case where it's just a multiple of 18. Okay. See, we switched to 18 here, not 19, because of the power of Fermat's little theorem here, this result. Okay. So the rest of it is fairly straightforward, folks. Here's just laws of exponents. 2 to the 6th power is 64. You can bring the k up. And then 2 squared is, of course, 4. Okay, 2 squared, I'll write it right above there, is 4. Okay. Now, this is very easy to see. 64, let me write it up here. 64 is congruent to 10. Right, folks? Because 64 minus 10 is 54, and 3 times 18 is 54. Okay? Now, a nice thing that happens here, and I'll just write it down. You guys can check it, or maybe I'll show you. But this is the same as 40. All right, which of course reduces to 4. Now, okay, now, and again, y'all notice that 2 to the 4th is 16, and we're essentially done with the problem. Remember, this is the exponent that we're applying to 2, so 2 to the 4th would be 16, and you would get the 16 that we're talking about right here, okay? So we're effectively done with the proof. If you're wondering how this happened, how we just removed the k right here and just said 10 times 4, notice that 10 squared is congruent to 10. Mod 18, okay? Mod 18, okay? Now, if you multiply through by 10, you get 100. 10 squared is congruent to 10, and so you get 10 cubed, okay, is congruent to 100, right? Let me put the congruence here. You see, we already know that that's, see how this builds? It's congruent to 10. See how it goes? And I'm not going to prove this formula. It's absurd to waste time on that. 10 to the 4th. Okay. In a similar fashion is also congruent to 10, right? 10 to the 4th is the same as congruent to 100 again, right? Because what I did, folks, is I multiplied 10 across this congruence. And you get 10 to the 4th is congruent to 100, which is congruent to 10. All right? And I'll put the vertical ellipses here. Okay, but you see how that works? So you get this, but remember this would be our r right here. Okay, this would be equal to our r. And then what's going to happen here? We've reduced this. Okay, we started with this and reduced it to 2 to the 4th. Okay, so I'll just it is. Let me just come over here. Okay. It is 2 to the 4th, mod 18, and we are done because that takes advantage of this truth right here, and we get the result we were seeking. Okay, so I'll go ahead and put QED. I've started writing a little bit less these days. I don't know if people like that very much, but we're done with the proof. QED. Because this 4 right here was applied became the exponent of 2. All right, which gives you 2 to the 4th, which gives you the 16 right here. Let me just write the 2 to the 4th there. Perhaps that'll help. Okay. All right, folks, that is all. Thanks for viewing.